Hello, I'm Christian from Group 12, and I'll be going over the first problem of Project 6, where we're looking at the microscopic structure of a gold-silver alloy. The first situation that we're looking at this microscopic structure under is where the alloy it was fast quenched. Or in other words, this alloy is rapidly cooled with some sort of fluid. Doing this process creates a less uniform structure within the alloy itself, or in other words, there's a smaller grain size for the individual metals within the alloy. For when this happens, the alloy has a higher hardness, but is also very brittle. To counteract this high hardness but increased brittleness, we can take the alloy through a process called tempering. This process increases the toughness of the alloy and the ductility. The next situation that we have is slow cooling. This process is essentially just annealing. During this process, the two metals have a lot more time to repackage themselves into clumps of their individual metals, or in other words, there would be a larger grain size. This process refines the crystal structure of the alloy and also makes it more workable by reducing the hardness of the material. Now I'll pass it on to Yuki to talk about question 2 of Project 6.
This is Project 6, Part 2 of Material Science. I'm Yuki from Group 12, and today I'll be talking about what phases are present in the gold-silver mixture, what is the mass of each phase, and what are the gold mass portion of each phase. So to start things off, the phase present at 1000 degrees Celsius is that it's a complete solid solution. At 1000 degrees Celsius, it's between the melting point of the mixture, between liquid and solid alpha phase FCC, silver to gold. And then the equation for weight fraction is R is equal to the overall composition minus the liquid composition, which equals 40 minus 33 equals 7. And then the solid one, which is S, equals to solid composition minus the original overall composition, which equals to 47 minus 40, and that would also equal 7. And R plus S is just 14, and you plug it into the equation on the right, which is WL equals S over R plus S, which gives you 7 over 14, and they'll both equal 0.5. So it's 50-50 solid and liquid. And then you would multiply them by the percentage. So it's 0.5 kilograms multiplied by 33, which would give you 0.165 kilogram for the liquid one. And then for the solid phase, it would be 0.5 kilogram multiplied by 747, and it will give you 0.235 kilogram, and you add them together for the total amount of weight, and they'll be 0.4 kilogram.
My name is Kylan, and I'll be doing part 3. So part 3 asks how we can create a brain mimic device using a gold-silver alloy, and it also asks which alloy would be better to use for the device. Would it be gold, silver, or copper, nickel? So first I'll explain how memory works in the brain, and I'll also explain the structure of gold to silver alloys. So brain memory relies on synapses, and synapses are places in the brain where neurons can communicate using electrical signals. And the plasticity of synapses can increase or decrease depending on how much they're used. The stronger the synapses are, the easier it becomes for electrons to communicate at them, which is how memory in the brain works. Now, gold and silver have very similar structures. When combined together in an alloy, these two very similar structures come together in a way where the electron paths don't align perfectly, and this causes the silver electrons to deflect off their conductive path. This is called electron scattering. And when the electrons deflect off of those paths, the path partially dissolves, which leads to the decrease in the alloy's conductivity. So to make the brain mimic device, using the gold-silver alloy, we can introduce a voltage to the alloy. This will cause the silver electrons that have deflected off of their path due to the electron scattering to create small conductive paths. When that voltage is turned off, the path will partially dissolve as the electron went back to drifting. When we reintroduce the voltage to the alloy, that partially dissolved path will be strengthened because drifting electrons will be able to access that path. Those partially dissolved paths are like memories in the brain. The more we turn the voltage on and off, the stronger the paths will become, just like synapses in the brain become stronger by the increased activity at the synapse. So the second question in part 3 was which alloy would be better for the device? Would it be a gold-silver alloy or a copper-nickel alloy? And in this case, it would be a gold-silver because the gold-silver alloy has a much higher conductivity than the copper-nickel alloy. And now I'm going to pass it on to Caleb for part 4.
My name is Caleb, and I will be going over question 4 of project number 6, in which I will demonstrate how to find the density of gold and silver in an FCC structure. For the density of gold, we have the mass of 196.97 grams per mole. We have a radius of 0.44 nanometers, and Avogadro's number, which is 6.022 times 10 to the 23rd atoms per mole. In order to find the length of each side, which in this example we will use A, we have to plug in the radius to the equation 4r is equal to radical 2a. After dividing by radical 2, we will get A is equal to 0.40729 nanometers, but we need that in centimeters. So we'll change that to 0.40729 times 10 to the negative 7th centimeters. To find the density, we will use the equation mass divided by volume. But in this case, we'll use the number of atoms multiplied by the atomic mass divided by the length of each side cubed, which is equal to the volume, multiplied by Avogadro's number. We will now plug in the numbers into our equation, in which we get 4 times 196.97 grams per mole divided by 0.40729 times 10 to the negative 7th power centimeters, and we will cube all of that, and we will multiply that by 6.022 times 10 to the 23rd power atoms per mole, and that will get us a density of 19.36 grams per centimeters cubed. Now I will demonstrate how to find the density of silver. When looking at the density of silver, we will see that the atomic mass is 107.87 grams per mole, and the radius is 0.144 nanometers. The Avogadro's number stays the same as that is a constant, and when we plug in to the formula to solve for A, we will get 0.40729 times 10 to the negative 7th centimeters. When plugging into the density formula, we will get 10.60 grams per centimeters cubed.